Hello everyone. Today we're going to continue working on a flexible cantilever beam. In the previous video, we simulated the cantilever beam under tip load and base excitation. So, what if we perform the experiment? Assume that we hang the stainless steel bar with one end attached to a linear actuator. To visualize this setup, think of a stainless steel ruler hanging vertically. To set this up properly, here are the material properties I'm using for the stainless steel bar. From the existing model, we placed it horizontally. So let's rotate the coordinate around the y-axis to hang it and set the gravity. Now, let's adjust the beam parameters. The beam width is h and the height is b. Then input the material properties here. Alright, this is what our beam looks like. The frame F1 here is the frame at midspan. I'll remove the forcing section because we're not going to use it. In this case, the beam will move in the x direction. So let's change the sensing coordinate and apply it to all. I'll use this gain block to convert the input unit to millimeters. Now, let's take a look at the input signal. The frequency came from the previous setup. And for the amplitude, I think 4 millimeters would be fine. Alright, let's see the simulation results. You'll see the beam deflect like this. Okay, now let's try forcing it at its natural frequencies. When you excite the beam at its natural frequencies, you'll see its mode shapes like this. Rho stands for mass per unit length, and the area moment of inertia can be calculated from this equation. The natural frequencies of this beam are shown here. Now let's try applying these frequencies. I'll start with the first mode. Let's see. You'll see the beam deflect like this. To verify that this is its natural frequency, I'll compare the amplitude at the tip. It's over 10.5 millimeters. Now, let's try 13 radians per second, which is higher than its first resonance. It's lower than 10.5 millimeters. Now try 11 radians per second. As you can see, it's also lower than 10.5 millimeters. That's it. This is how to quickly verify a resonance. Anyway, if you think you cannot see the deflection clearly enough, you can adjust the damping to be lower. Actually, you should measure the damping from the experiment. For example, through a free vibration test, or look it up in a textbook. But for this video, I just randomly assigned the values. Now let's try the second mode. Let me just slow it down. You'll see the node here. It behaves like this. Now, let's go for the third mode. Its amplitude is going to be small, so I'll use 10 millimeters. You'll see its shape looks like this. It has two nodes. I think it's not clear enough. Let's try the higher amplitude. So we might apparently see these nodes. Let's try 15 millimeters. If you think it's not clear enough, you can assign a lower damping value. Let's see. I think it's too low damping. When you use very low damping, its equations become numerically stiff. You can use a stiff solver or just increase damping to make it faster. This is good. You can see the shape more clearly. It has nodes here and here. This is how the third mode looks. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.